Hello, my name is Gernot Ziegler. I'm here from Vienna in Austria. I would like to talk today about a project I've made. I call it an open investigation. First, a little bit about my background. I've worked for 15 years in GPU, general purpose computing on the GPU, especially in computer vision. First at the Max Planck Institute for Informatics for 5 years, and then I started working for NVIDIA for 7 years. Recently, I've founded my own company, a freelancing company, a consulting company in exactly that area, which goes all the way from volume compression, ray tracing to computer vision for automotive. The main focus is on computer vision and visual computing, that is GPU-based computer vision algorithmics, light field acquisition and rendering. The open investigations I do are sometimes on a topic that I find interesting, that I just had an idea about. There might not be a customer yet, but you can just put it in your toolbox and maybe later you can present it to someone, or it makes a good demo for the portfolio for your homepage later on. There are several demos on my homepage. Only the one that I've showing you here is exposed now at the moment. Usually I just send the private links around. This current talk is going to be about general purpose computing on the GPU, where I mix real-time game graphics techniques, that is Z-buffer, occlusion, culling, and shadow mapping, with general purpose computing. The general purpose computing part is rather simple here, but it can be extended later on too. I just wanted to show you, I think the important thing is here shadow mapping and texture domain mapping. How many of you have programmed OpenGL already? Quite some. Okay, that's not hard then. Okay. So, all right, then I can fast forward on things, and maybe it takes less than 20 minutes anyways, with all your background knowledge. What I wanted to talk about today is the task setting I thought about some months ago is I played with my HTC Vive at home and thought, it would be really cool if I could have a landscape, for example, that I've reconstructed with photogrammetry, and then change the light position, the sunlight position, so to say, depending on the day, depending on the season. But of course, that is what everyone does, and that's what architects also are using in their CAD software. What has not been done so often is to accumulate the sunlight over a certain amount of time, because that usually takes a lot of computation with the CPU. That means that you can take a certain time range and then simulate the sun position and then be able to tell how long the sunlight has exposed every single surface area or pixel in the landscape. So this shall show now how I acquired the footage, created a 3D model, and then how I implemented it on the GPU. So the input that I have, or one will have, is a landscape 3D model and the GPS position of the actual, where it was taken, where the footage was taken. I would like to know afterwards how many hours per day the landscape and its buildings were in light. Two possible uses, just as an example, would be, for example, solar panel planning, where you want to tell for hard, that is half occluded areas, how many hours of sunlight you can still attain there. Or you could also use it in construction planning. I've talked to a friend that is an architect, and he tells me that one of the task settings they have there is if you have a larger building, you want to verify that the lower floors in the building actually have enough sunlight for over the course of a year. In this case here, we took the landscape of Porto San Giorgio in Italy, and we wanted to record the remnants of the city walls. So for that, we took a Parrot Bebop 2 drone that recorded video. We thought we were very professional with that, but I guess we were still a little bit layman about it, but at least we got some frames, video frames out of it. And the example video frames were of pretty good quality. Some were overexposed, some were not so good, like here. But still, it was good enough footage to feed it to the photogrammetry software. For the reconstruction software, we use a software called Reality Capture that originates from Bratislava. It's a pro-level photogrammetry software that you can use the GPS information from the frames and, of course, the photo correlations in between the different video frames to reconstruct the camera positions, to reconstruct sparse point clouds, and then also to reconstruct a dense 3D mesh that is textured. So you take all these video frames that you have extracted from video, you feed it to reality capture. Unfortunately, it doesn't take videos per se, but extracting video frames is good enough. This way you can also do a little bit of quality selection of the best frames. Then your GPU compute for some minutes, and the photogrammetry software reconstructs the color texture of the landscape from the camera views by assuming that there is a photo consistency. That means that there is a color agreement between the camera views, and it also takes care of the occlusion, of course. So what you get out of this is a result like this, and I can show it to you quickly also in the software. If I would see my, here it is, here you go. So this is what it would look like, right? And the white you see here is the reconstructed camera positions for these 918 video frames. So that's a very nice thing to do in this software. Usually it would then export a wavefront OBJ object with the color texture. It can also export the camera positions. I don't need them here in this case. And so let's continue the presentation. What happens then? So after we have obtained this 3D model, we want to bring it to the screen and display it in our own application. So we use a WEBGL to ensure, I've chosen here WebGL to ensure platform portability. Of course, you can use any other 3D API. I like that because you can use it on mobile, desktop, and even VR. So there's actually this link that the application, where the application can be found, even runs on the cell phone. I use the canvas element in HTML5, but instead of creating a 2D drawing context, I acquire a 3D context, a WebGL2 context. And WebGL2 is programmed with an OpenGL-like API in JavaScript, but it's pretty similar to the C API that you know from normal C executables. Well, then you can draw it, and this is what it looks like for a start. The interesting thing is, of course, that the mesh would usually be really large to download from the server every time. This runs here on my laptop at the moment, but in general, the mesh would be 27 megabytes for 300,000 vertices. I used the Google Draco mesh compression algorithm to reduce this down to 1 megabyte. I can really recommend that. So let's get back here again. So the texture, the landscape color texture in this case is 4 megabytes for the 4000 times 4096 resolution. From reality capture could also output 8192, but it's not necessary here. Now, where is the sun in relation to the landscape model? We would obtain the GPS position from the drone, and then, well, just for safety reasons, verify it with Google Maps. And yes, you see the tower and the remnants of the city wall exactly here. The next thing is we need the sun position. There's a very nice tool on sunearthtools.com, which gives the GPS position from the drone, and it yields then, by selecting, I can't remember where it was, somewhere here on the webpage, I can show you afterwards, we can look it up together, a CSV file or Excel file with the sun position of 2017, for example, at 5 minutes granularity, with an azimuth and elevation vector for every single sample. So that provides us with the sun position in relation to the tower and the city walls. Now we would subdivide the sun exposure into time steps. The question is now, how do we get to the heat map? That's what I wanted to say. We would first subdivide the sun exposure into time steps and simulate the sun position for every single time step. I can do that here in the app, and again I lost here better. So let's see my wonderful key combinations here. Yes, here we go. So that would be the sun. Yeah, I'm not very good at rendering suns. You can gladly show me more about that. But this is the accurate sun position for that very position. I know that at least. So back to the presentation. Now, how to find out how the sun landscape is exposed to the sun over time. How can we determine that the rendered pixel is in shadow or not? Shadow computation in rendering is basically a visibility computation. So you would first check if the pixel is visible from the light source view. And for that purpose, one would render the depth map from the light source into a virtual camera that is a representation of the light source's viewing point. And in the sun's case, this is an orthogonal camera because all the sun's rays are parallel when they approach or reach the Earth. So that means that we now have the kind of a color map or depth map available from the sun's view. And the second step is now that when one renders the scene, you transform each of the pixels' 3D position into the light source's virtual camera's projection space. So you render the scene from this view that you see here, but you also take every pixel's 3D position and transform it into the projection space of this very of the light source's virtual camera. Then you do a shadow depth map value with lookup and compare it with the pixel's current depth value that has originated from this transformation. If it is near identical, then the pixel is in light. If it is smaller, then the pixel is not visible to the light source, so the pixel is in shadow. So now we would like to accumulate this sun shadow over several sun positions. The problem is, though, that the shadow mapping only, the current one that we have seen previously, only computes the sun visibility for user-visible pixels, so the ones that are currently visible on this scene. But if we do the same thing for the heat map, that means accumulate all these partial sun visibility samples, then we wouldn't be able to finally rotate the heat map because the heat map would only be specific for this very viewport. So the solution is here. To move the heat map computation to the texture domain instead. Now a bit about textures might bore some of you. I hope that's not too, it doesn't take long. So the point is here that the texture, the surface texture of the landscape is parameterized and stored in a 2D map, 2D texture map. And each of these vertices on the triangles have a texture coordinate, a 2D texture coordinate, from which you can more or less make a lookup into the color texture to get it back. Now, in order to color the scene, the renderer would then make a lookup into the texture domain's texture map, color texture map that the photogrammetry software has reconstructed, and then put it over into the view domain. So this is the usual rendering that you would get. Now the fun thing is that the GPU can also write to this domain, can write to the texture domain by itself. So that is actually DETOUR. I'll mention that later. So instead of rendering the heat map or trying to compute the heat map in the view domain, we would take all the landscape mesh triangles and put them into the texture domain, where we compute the sun visibility for the current sun position. So the output in the texture domain is a visibility value 0.01 or 0.0 for the current sun position, which is similar to the shadow mapping. Let me show that to you here in the app. So what we have here is right, interesting. That doesn't work. Nice, okay. Right, wonderful. Okay, I have no clue what's happening. Okay, we can go to the texture domain. That works at least, but the other switch doesn't work. Let me reload that. Maybe that helps. Yeah, right, here we go. Okay, so here is the shadow visualization, and the sun was obtained here, again, a sun. And if you move it, you see how the shadow mapping works. And by transforming all these triangles back into the texture domain, you can see that the shadow computation can also happen in the texture domain. Doesn't really matter that much. Okay, going back again. So, back to here. Now, how does this heat accumulation happen in that case? Well, you would just iterate from the start time to the end time and repeatedly repeatedly render the landscape mesh triangles into the texture domain and use the OpenGL blend node to add this visibility value, this shadow map value, well, the shadow comparison result, to the frame buffer value. And this is done with the OpenGL blend function 1.1. So the shadow map test by itself is not very large. Of course, with all the surrounding rendering, pipeline around it. But more or less, you take the shadow position that you have previously transformed into the light source's projection space. Do some math on the projective texturing, and then you have a comparison between the shadow position of the actual pixel. If it is less than the depth value of the shadow map lookup, then with some margin factor, then you would output a 0.01. Otherwise, it's 0.0. That's it. So, how does this look here? I'd rather reload again. Yes, it would be nice to actually get my link back. That's very nice, thank you. So, here you go. So my wonderful sun back here, right? Heat map accumulation. And this is what happens afterwards. So, all right. So yeah, that's it more or less. The point of it that I wanted to mention here is that you can do shadow computation on the CPU. It's no problem for a single view. But if you really want to go into simulations over time, where you have to accumulate, say, over a day or a month or a year, then it is useful to use the GPU for that. The GPU can contribute with the visibility, with the occlusion. It can also with the rasterization that actually also handles the occlusion, and the shadow map lookups. And the second thing is, of course, it has massive data bandwidth available, so all these computations in high resolution are no problem if you have 300 gigabytes per second to a memory bus. So if you want to pursue something in this direction or similar, let me know. I might be able to give you some input and ideas on further extensions of this. Some things that I've thought about extending or using it for is the self-occlusion, well, in general, for architecture, for solar panel construction, and there was a third one I can't remember now. Okay, I'll come up with it later. The point is that you can really do a fast simulation. The GPU is able to simulate that within seconds, and makes the thing interactive. So an architect that wants to, for example, have a building and is not sure about the sun exposure in the lower floors can modify the building interactively, and the GPU is able to simulate it within 1 second or two. So if you have any suggestions on how this can be used in other applications, please let me know. And other GPU questions are also well addressed with me. Thank you very much.
Any questions? How did you handle the real sun that was in the pictures already?
The real?
The real sun that was already in the pictures when you were taking them.
The real sun? Photogrammetry takes care of that. If you have enough samples of the same object from different angles, then it's usually no problem. It has some kind of averaging where it takes out the samples that are too far from it, so to say.
Light.
Yeah, the light.
The sun.
The light, yeah, the overexposure. You mean in the sun?
Ah.
Oh, you mean right. You mean when you reconstruct the color texture. Yes, of course. You need to account for that later on too. That's what I actually have in the later work. That is not trivial to do. That's well, you would compute the original sun. You would have to take the sun position when the whole thing was recorded, and then you would have to subtract it from the texture afterwards. Yes, I didn't do that here. No, that's true.
One short one.
So 2 short questions. One question is, do you consider non-Lambertian surfaces? And second, do you consider indirect light when you model lighting?
One moment. Lambertian surfaces. Well,
Non-Lambertian.
non-Lambertian surfaces.
Yes.
You mean specular reflection or similar
Yes.
behavior? Well, it doesn't matter for the occlusion computation, for the visibility computation. It would matter for the photogrammetry reconstruction, you mean?
Exactly.
That's right. Well, photogrammetry is mainly used here to reconstruct the 3D mesh. The accurate color texture is not so important here. This is only about the occlusion computation. But you're right, if you want to really recompute, if you want to compute proper material behavior or similar, you need to take the camera positions that have been reconstructed by the photogrammetry software, look at each texture surface pixel, more or less, and then see which cameras have seen it, and also then compute what kind of samples you have from different directions, because you know the original camera position. So this way, and combined with the sum position, you can then actually start to guess or start reconstructing the material property. I have one link to Vlastimil Hadran in Prague that can tell you more about that.
What about, yeah, thank you. And what about indirect light, when you actually simulate the occlusion?
Flight?
Indirect light.
Indirect light, yes.
Like global
okay,
illumination.
that would mean on top of that you would have to simulate, what's it called? Indirect lighting. That would mean that you would have to compute the connection between the surfaces on the mesh, how they are connected with each other, and start to make a global illumination simulation or similar. Okay. Or we can talk about it afterwards too.
Let's thank Gernot again.